Hi everyone, welcome to the video for Module 7.2.4, continuing with the electrophysiology. We're getting to the action potential here. And this is a rather long one, as the action potential is fairly important in describing skeletal muscle innervations and the passages of the neural pathways. So an action potential is a propagated changes in the membrane potential that once initiated affect the entire excitable membrane. These electrical events are also known as nerve impulses. And recall that voltage-gated sodium channels are abundant in the axon, its branches, and the axon terminals. So the first step in generating an action potential is the opening of the voltage-gated sodium channels at one site, which is usually the initial segment of the axon. And the movement of sodium channels into the axon depolarizes the adjacent sites, which then triggers the opening of the additional voltage-gated sodium channels. And this result is a chain reaction that spreads across the surface of the membrane, like a line of falling dominoes in a way. So like this, the action potential is propagated along the length of the axon, ultimately releasing and reaching the axon terminals. We can highlight something called the all or none principle here, and the membrane potential at which the axon potential begins is called the threshold. And the threshold for the axon, like we've talked about before, is typically between minus 60 millivolts and minus 55 millivolts, which corresponding to a depolarization of 10 to 15 millivolts from the resting membrane potential of 70 or minus 70. So a stimulus that switches the resting membrane potential from minus 70 to minus 62 millivolts will not produce an action potential, only a graded depolarization. And when the stimulus is removed, the membrane potential will return to that resting level. And the depolarization of the initial segment of the axon is caused by local currents resulting from the graded depolarization of the axon hillock. The initial depolarization acts like a pressure on the trigger of a gun. So if you apply a slight pressure, the gun doesn't fire. It only fires when you apply a certain minimum pressure to the trigger. So once the pressure on the trigger reaches this threshold, the firing pin will drop and then the gun will discharge. At that point, it no longer matters whether you applied the pressure gradually or suddenly, or whether you just moved one finger or clenched your entire hand. The speed and the range of the bullet that leaves the gun does not change, regardless of the force that you applied to the trigger. In the case of an axon, or another area of excitable membrane, a graded depolarization is similar to the pressure on the trigger, and the action potential is like the firing of the gun. All stimuli that bring the membrane to threshold generate identical action potentials. So in other words, the properties of the action potential are independent of the relative strength of the depolarization stimulus, as long as the stimulus exceeds that threshold. So this concept is what we call the all or none principle. And because a given stimulus either triggers a typical action potential or none at all, the all or none principle will apply to all excitable membranes. This diagrams the steps that are involved in generating the action potential from the resting state. So at normal resting potential, the activation of the gates of the voltage-gated sodium channels are closed. And the steps are kind of as follows. One is the depolarization to threshold. Two, the activation of the voltage-gated sodium channels and rapid depolarization. Three, the inactivation of voltage-gated sodium channels and activations of voltage-gated potassium channels. And four, the closing of those voltage-gated potassium channels. Speaking of the generation of an action potential. So in step one is a depolarization to threshold. So the stimulus that initiates an action potential is a graded depolarization large enough to open the voltage-gated sodium channels. The opening of the channels occurs at a membrane potential known as the threshold. Step two is the activation of the sodium channels and rapid depolarization. So when the sodium channel activation gates open, the plasma membrane becomes much more permeable to sodium, which is driven by the electrochemical gradient. Sodium then rush into the cytoplasm and rapid depolarization occurs. The inner membrane surface now contains more positive ions than negative ions, and the membrane potential has changed from minus 60 millivolts to a positive value. Step three is the inactivation of sodium channels and the activation of potassium channels. So as the membrane potential approaches positive 30 millivolts, the inactivation gates of the sodium voltage-gated channels close. And this step is known, as we talked about, as the sodium channel inactivation. And it coincides with the opening of voltage-gated potassium channels. Positively charged potassium ions move out of the cytosol, which then shifts the membrane potential back towards resting level, and repolarization begins. In the fourth step, which is the closing of potassium channels, the voltage-gated sodium channels remain inactivated until the membrane has repolarized to near threshold levels. And at this time, they regain their normal status. They're closed, but they're capable of reopening. The voltage-gated potassium channels begin to close as the membrane reaches its normal resting membrane potential, minus 70 millivolts. And until all of these potassium channels have closed, the potassium ions continue to leave the cell, which produces a brief period of hyperpolarization. So the plasma membrane does not respond normally to additional depolarization stimulus from the time an action potential begins until the normal resting potential of the membrane has stabilized. This period is known as the refractory period of the membrane. The membrane cannot respond to further stimulation from the moment the voltage-gated sodium channels open at the threshold until the sodium channel inactivation ends, because all the voltage-gated sodium channels either are already open or they're inactivated. In this first part of the refractory period, called the absolute refractory period, which lasts from about 0.4 to about 1 millisecond, the smaller the axon diameter, the longer the duration, and we'll get into that a little later. The relative refractory period begins with the sodium ion channels regain their normal resting conditions and continues until the membrane potential stabilizes at resting levels. Another action potential can occur in this period if the membrane is sufficiently depolarized. And that depolarization, however, requires a larger than normal stimulus because of a couple reasons. The local current must deliver enough sodium to counteract the exit of positively charged potassium through the voltage-gated potassium channels. And two, the membrane is hyperpolarized to some degree throughout most of the relative refractory period. And this is just a summary of what we just talked about in the generation of action potentials. So the events that generate an action potential take place in a small portion of the total plasma membrane surface, but unlike graded potentials, which will diminish rapidly with distance, action potentials spread along the entire excitable membrane. And to understand how this happens, imagine that you are standing on the doors of a movie theater at the start of a long line. So for example, everybody's waiting at the doors to open. The manager steps outside and says to you, "Let everyone know that we're open in about 15 minutes. How would you expect to spread the news? If you treated the line as an excitable membrane, you could shout, "The doors are open in 15 minutes," as loudly as you could. The closest people to the line would hear the news very well, but the further away might not hear the entire message, and those at the end of the line might not hear you at all. On the other hand, if you treated the cloud as an excitable membrane, you would tell the message to the next person in line with instructions to pass it on. In that way, the message would travel along the line undiminished until everyone had heard the news. And then such a message moves as each person repeats it to someone else. And distance in this case is not a factor, whether the line contains 50 or 5,000 people. So having each person repeat the message is comparable to a way the action potential spreads along the excitable membrane. An action potential or the message is relayed from one location to another in a series of steps. At each step, the message is repeated, but because the same events take place over and over again, the term propagation is preferable to the term conduction, which would suggest a flow of charge similar to that of conductor, such as copper wire. In fact, compared to wires, axons are poor conductors of electricity. But action potentials may travel along an axon by continuous propagation, or unmyelinated axons, or by saltatory propagation, or myelinated axons. We're going to get a little more in depth into the propagation of action potentials here. So in one, we're going to talk about continuous propagation or the degree of myelination to these. So in an unmyelinated axon, the action potential moves along by continuous propagation. For convenience, think of the plasma membrane as a series of kind of adjacent segments. If the action potential begins at the axon's initial segment, for a brief moment at the peak of the axon potential, the membrane potential becomes positive rather than negative. And this can occur in two steps. So a local current then develops as a sodium ion begins to move into the cytosol and the extracellular fluid. The local current then spreads in all directions, depolarizing adjacent portions of the membrane. The axon hillock cannot respond with an action potential because, like the rest of the cell body, it lacks voltage-gated sodium channels. And this process continues in a chain reaction. In that step 3, the action potential will develop at that location, and the next initial segment will enter the refractory period, like we've talked about. In step 4, that local current depolarizes in the adjacent portion of the membrane to threshold, and the cycle is then repeated. And each time a local current develops, the action potential moves forward but not backwards. but because the previous section of the axon is still in the absolute refractory period. As a result, the action potential always proceeds away from the site of generation and cannot reverse direction. And eventually, the most distant portions of the plasma membrane are affected. So in the movie line example, the message is relayed from one location to another. At each step along the way, the message is retold, so the distance doesn't have an effect on the processed. The action potential reaching the axon terminal is identical to one generated at the initial segment, and the net effect is the same as if a single action potential had traveled across the surface of the membrane. So in continuous propagation, the action potential appears to move across the surface of the membrane in a series of tiny steps, and even though the events at one location only take about a millisecond, they must be repeated at each step along the way. Continuous propagation along unmyelinated axon occurs at the speed of about 1 meter per second. So for a second action potential to occur at the same site, a second stimulus has to be applied. Saltatory propagation is a little different. So in the CNS and PNS, it carries the action potential along the axon much more rapidly than does continuous propagation. And to get the general idea, we can go back to that movie line where we're in the front of the movie theater and assume it takes about 1 second to relay the message to another person. So in a model of continuous propagation, the people are jammed together. In 4 seconds, 4 people would hear the news, and the message would move perhaps 2 meters along the line. So in a model of saltatory propagation, however, the people in the line are spaced about 5 meters apart. So after 5 seconds, the same message would move 20 meters, so much faster and cover much more distance. And this just highlights some of the steps of saltatory propagation. So active potential occurs at the initial segment. Step 2, depolarization to the threshold. Step 3, the action potential at node 1. And then step 4, the depolarization to the node at step 2. This graphic just highlights some of the differences between graded potentials and active potentials. So myelin greatly increases the propagation speed of action potentials. The diameter of the axon also affects the propagation speed, although less dramatically. Axon diameter is important because ions move through the cytosol in order to depolarize adjacent portions of the plasma membrane. Cytosol offers much less resistance to ion movement than does the plasma membrane. And in this instance, an axon behaves like an electrical cable. So the larger the diameter, the lower the resistance. And that's why motors with large current, such as the starter on a car, or electric stove, or a big air conditioner, use very, very thick wires. We can classify axons into 3 groups according to the relationships among the diameter, myelination, and propagation speed. So type A fibers are the largest myelinated axons, with diameters ranging from 4 to 20 micrometers. And these fibers carry action potentials at speeds of up to 120 meters per second, or about 268 miles per hour. Type B fibers are smaller myelinated axons with diameters of about 2 to 4 micrometers, and their propagation speed average around 18 meters per second to about 40 miles per hour. And then type C fibers are unmyelinated and less than 2 micrometers in diameter, and these axons propagate action potentials at the leisurely pace of about 1 meter per second or about 2 miles per hour. So the advantage of myelination becomes clear when you compare type C to type A fibers, and note that the diameter increases tenfold, but the propagation speed increases 120 times. So type A fibers carry that sensory information about position, balance, and delicate touch and pressure sensations from the skin surface to the CNS, the motor neurons that control skeletal muscles, and also send their commands over large myelinated type A axons. Type B fibers and type C fibers carry information to and from the CNS. They deliver temperature, pain, general touch, pressure sensations. They also carry instructions to smooth muscle, cardiac muscle, glands, and other peripheral effectors. So why isn't every axon in the nervous system large and myelinated? The most likely reason is that it would be physically impossible. If all sensory information were carried by large type A fibers, your peripheral nerves would probably be the size of a garden hose, and your spinal cord would be the diameter of a garbage can. Instead, only about 1/3 of all axons carrying sensory information are myelinated, and most of the sensory information arrives over type C fibers. In essence, the information transfer in the nervous system represents a compromise between propagation time and available space. Messages are routed according to propriety, or basically urgent news or sensory information about things that threaten survival and commands that prevent injury, travel over type A fibers, so the equivalent of instant messaging or texting. And then less urgent sensory information and motor commands that are relayed by type B fibers, such think of it kind of like email, or type C fibers as getting a letter in the actual mail. There's also a disorder here that we can talk about, which is multiple sclerosis or MS, which is the genetic disorder that affects the myelin on neurons in the PNS.